to the next lecture, which is going to be about shifting theorems. Shifting theorems are two relations that are used to find a Laplace transform and find inverse Laplace transform in special circumstances. And most of the time we're going to use these theorems to find inverse Laplace transforms of the functions that we're going to get while we'll be solving inverse initial value problems. So let's get to it. The first theorem says the following. It says if we have a function f of t that has a Laplace transform, let's call it capital F of s, then a slightly modified function that is just pre-multiplied by a factor e to the alpha t, that slightly modified function will have a Laplace transform that is just shifted to the right or to the left by value of alpha, depending on what alpha is. This theorem poses no restrictions on alpha. The next theorem will actually restrict the values of alpha to be strictly positive. Let's prove the theorem. Well, the proof is, unlike many other theorems, is extremely easy. You just compute the Laplace transform and see what it is. The Laplace transform is just an integral from 0 to infinity of e to the alpha t, f of t, multiplied by e to the minus st, the whole thing integrated with respect to t. I can bring the e to the alpha t and e to the minus st together, and that will give me an integral from 0 to infinity of f of t multiplied by e. I'm going to keep the minus sign inside, so minus sign outside of everything, and put the alpha inside the parentheses. And this integral seems like it is the Laplace transform, but the only difference is that instead of a parameter s, this Laplace transform has a parameter s minus alpha. And that means exactly the following, that it is the Laplace transform of f with s minus alpha plugged into it. And it's really that simple. So we see that multiplying by e to the alpha t in the time domain, in the function domain, in the signal domain, means that in the Laplace transform domain, in the S domain, we just have a shift by value of alpha. The other theorem is very similar. Instead, we're going to do the shift in the time domain this time. So suppose a function f of t has a Laplace transform capital F of s, and the Laplace transform of a shifted version of f, and I'm going to give a lot of space here, and you will see why. So how do we shift functions to the left or to the right? Well, we just subtract the value of the shift from the argument of the function. And this is the effect that is achieved. If I have a function that is something in terms of t, and so this is f of t, and we just shift it by value of alpha, so this is going to be the shift. Well, the function is just going to repeat its values, but now they're going to be all the way to the right. And here's an interesting thing. Well, my function was initially 0, but what if it isn't? What if the formula for that we use for the functions, say like sine or cosine, that formula gives non-zero values for negative t values. So when we shift it to the right by a factor of alpha, those non-zero values will start appearing for values of t that is greater than 0. So in order to prevent this, what we do is we artificially, the functions being the Laplace transform changes a little bit, and you might have already guessed that the change is going to be just a multiplication of the factor with e to the alpha in something, and it is. It's just e to the minus alpha s. So we see here that there is a duality between these two theorems. When we multiply by exponential function f of t, we get a shift for the Laplace transform. When we shift in the time domain, we get exponential multipliers in the Laplace transform domain. The proof is extremely simple. All we have to do is just compute the Laplace transform. The integral is going to be slightly longer than before, but it's all the same. So Laplace transform of this whole thing is going to be the integral from 0 to infinity of this monstrosity times e to the minus st. We can easily see, because h t minus alpha, and I apologize, I forgot to mention explicitly that alpha has to be greater or equal than 0, and that is important. We only shift to the right. Well, because h of t minus alpha is 0 all the way up to alpha, we can consider it to be the same as the integral from alpha to infinity of this function. Well, then we're going to employ a change of variables. I'm going to introduce a new variable tau that's just t minus alpha, and therefore t becomes tau plus alpha, and dt is the same as d tau. Then we have to also take care of the limits of integration, and that means that we have to figure out what is tau when t is alpha. Well, that's simply 0. And what is tau when t goes to infinity? Well, that's the same. Tau also goes to infinity together with t. Yes, I cannot plug in t equals infinity into the formula for tau just because that's not the correct calculation. When we're dealing with infinities, we always have to consider a limit. Alright, that changes my integral into the integral 0 to infinity. Now it's going to be h of tau f of tau e to the minus s, while t changes to tau plus alpha d tau. Because h of t is 1 when tau is greater than or equal to 0, then that's just simply the integral from 0 to infinity of f of tau e to the minus s tau, and I'm going to break the exponential function apart times e to the minus s alpha d tau. E to the minus s alpha is independent of tau, that can be factored out. And the inside is just f of tau e to the minus s tau d tau. And it's now very obvious that this integral is exactly the Laplace transform of f. The fact that we changed t to tau here does not make any difference because the integral has exactly the same form. The name of the internal variable for the integral does not change the value of the integral. So this is simply e to the minus s alpha times capital F of s. And that's the end of the proof. These proofs are actually quite different from many other proofs, and you see in mathematics, these are just proven by performing the calculation. Anyway, I'm giving you the proofs so that you have a context for those theorems, so you know they're true, and that's all you need to know. I will not ask you to prove anything or to use the parts of this proof or replicate parts of the proofs for any of the tests. I'm just giving it to you to provide context. There's a couple of remarks that I want to make here. One is that we can see that there is a peculiar duality between these theorems. Which means multiplying by an exponential factor in one domain leads in a shift of another domain. So shift in t is the same as the exponential factor in s, and multiplying by exponential factor in t means shift in the s variable. Another thing, most of the time we're not going to be using these theorems to find Laplace transforms. Most of the time Laplace transforms are used to solve initial value problems or to help solve control problems, and for these problems the Laplace transform of a signal is a given function, and that signal passes through a certain electronic black box or something like that, some certain thing that has a mathematical model for it, and what comes out is the value of interest. And most of the time the Laplace transform of that signal changes in a certain way, and when you have to find the inverse Laplace transform, and that's where the shift theorems are mostly used. So I want to say that shift theorems predominantly are used to compute inverse Laplace transforms. And this is where we will see expressions of this form getting changed into some weird combinations of functions and Heaviside functions multiplied by them. Alright, so let's consider a few examples. When we have piecewise functions, integrating it through usually breaks into integrals over several subdomains, and it's not always easy to compute. So instead, we can use the language of the second shift theorem, multiplying things by Heaviside functions, to express a piecewise function as simply a sum of shifted versions of functions. How do we do this? I'm going to illustrate with this simple turn on and turn off function. If you try to plot this function, That's how this function looks like. So this function is 0 all the way up to t equals 1. Then it jumps up to t value 2, where it stops being 1, jumps to 0, and just being 0. So the goal is to express this as a sum of Heaviside functions. Why is it important as a sum? Because it's also possible to express it as a product of two Heaviside functions, one being sort of reflected. And in that way, the reflections are not very useful because the Laplace transform does not treat reflections very favorably. It does not treat products of functions very favorably. Products of functions result in convolutions of the Laplace transform, something we're going to discuss later. So if I express it as a sum of two Heaviside functions, that will be a very easy characterization for us because we'll be able to find Laplace transforms of those extremely easy. So let's just do it. So what combination of Heaviside functions will achieve this? Well, as you know, the standard Heaviside function just turns on at 0. So what I need for the functions f of t, let me switch the color here. What I need for the function f of t is to have a shifted version of Heaviside function. And obviously, I need to shift by 1. And there's going to be something else added to turn it off at 2. So this part, h of t, will turn on at 1 and will always be 1, even past 2. So something should happen at 2 to bring it back to 0. And if I can't change the h of t, it's always going to be 1. The only way to change it with the addition of a term is to add something that will be -1 at 2. So I need to add something that will become -1, but only become -1 at exactly 2 and will continue onward. Well, that seems that I will have to add a function that is 0 all the way up to 2 and then -1 right after. So what I need to do is I need to add a Heaviside function shifted to 2 and then multiplied by -1. So it's simply h of t minus 1 minus h of t minus 2. And that does the trick. This function will turn on, become 1 at 1, and then will turn off at 2. And I'll demonstrate it with Mathematica how it all plays out later on. So what's the Laplace transform of this? Well, that is simply the Laplace transform of h of t minus 1 minus Laplace transform of h of t minus 2. In the previous lecture, we computed the Laplace transform of these shifted Heaviside functions. But we can also use shift theorems to get the same result. So standard h of t, so that's going to be simply e to the minus alpha, which is in this case 1, minus s times the Laplace transform of just the Heaviside function minus, here we're shifting by 2, so it's minus 2s times the Laplace transform of Heaviside function. And the Laplace transform of Heaviside function is 1 over s. So this simply becomes e to the minus s minus e to the minus 2s divided by s. And that's the Laplace transform of this thing that turns on and turns off. Alright. It's also easy to see that with this function, which is that simple, we can compute the Laplace transform directly. We can use the definition of Laplace transform, and just integration from 0 to infinity will turn into integration from 1 to 2 and give us exactly the same result. However, I wanted to demonstrate how we can construct a turn on and turn off function with two Heaviside functions, because that's going to be very useful later on when our signal becomes piecewise defined. For example, let's look at the g of t, which is defined as a sine function. But only for a short period of time. It's a sine function, starts at 0, goes all the way to 1, comes back to 0 at pi, becomes -1, becomes 0 to pi, and then from then on continues as 0. In this case, I could use the definition of the Laplace transform and convert the integration from 0 to infinity to integration from 0 to 2 pi only, and again I would have to use the integration by parts twice, and it's going to be quite a complicated integration. Instead, I could just use the existing formula for the Laplace transform of sine, and then break this function into a sine of t multiplied by two Heaviside functions that turn it on and turn it off at 0 and 2 pi. So g of t can be expressed as sine of t multiplied by h of t will make it turn on at 0 minus h of t minus 2 pi. So this ends up being h of t sine of t, which is simply sine of t, because again Laplace transform does not care about what happens before 0, minus h of t minus 2 pi times sine of t. Well, the second term here does not look like the full-blown shift. It looks different. We have to make it look like a shift, and that means I would have to change sine of t into some combination of functions of t minus 2 pi. Well, if this turning off happened somewhere else, not at 2 pi, then that would be somewhat difficult, but we're lucky because 2 pi is exactly the period of sine of t, and so we can just write it as h of t times sine of t minus h of t minus 2 pi times sine of t minus 2 pi. Well, that means that the Laplace transform of g of t is just a Laplace transform of a standard sine function minus the Laplace transform of a shifted sine function. Well, the Laplace transform of sine is omega over s squared plus omega squared, where omega is 1, so in this case it's just going to be 1 over s squared plus 1. And for the shifted, it means we just multiply by e to the minus 2 pi s divided by s squared plus 1. So we can join it together into 1 minus e to the minus 2 pi s divided by s squared plus 1. Simple, isn't it? Alright, the last function doesn't look like a shift. It looks like a function sine of t times cosine t multiplied by an exponential factor. Well, we don't know what the Laplace transform for sine of t times cosine t is, but with the help of a little bit of trigonometric formulas, we can easily convert it into the following. So, sine t cosine t is exactly 1/2 sine of 2t. So now we can use the first shift theorem to compute the Laplace transform of this. So it's going to be, well, e to the minus t is shifting by alpha being here -1, so it's going to be changing s into s plus 1. So this is going to be the Laplace transform of 1/2 of sine of 2t. And then after that, s will be replaced with s plus 1. Well, what is the Laplace transform of the sine of 2t? Well, that's 1/2 times 2 over s squared plus 4, with s being replaced with s plus 1. So this becomes, well, 2 and 1/2 cancel each other out, becomes 1. Then s changes into s plus 1 squared plus 4. So this becomes 1 over s squared plus 2s plus 1 and plus 4, so plus 5. And that's the Laplace transform of this function. For the first homework, you will have to do something similar to that. You can use the definitions, you're more than welcome to use the definitions, but I'm pretty sure it's going to be a lot easier if you use these shifting theorems to solve the problems. Well, I said earlier that these shifting theorems are used to find the inverse Laplace transform, and let's do just that. We have a Laplace transform, and we can immediately see that there is an exponential multiplier, which means that the original function was shifted by alpha 1. So what we can do is we can do the inverse Laplace transform of just the fractional part, and then shift the t by 1 at the end. So let's do inverse Laplace transform of s over s squared plus 4s plus 5. And the form of this seems very, very similar. We see in the previous problem a very similar form right here. We have s squared plus 2s plus 5, and we see that this came from sine. So what we have to do here is we have to complete the squares in the denominator and see what happens there. Well, the completion square is very easy. It must be s plus 2 squared. Well, s plus 2 squared takes care of s squared, 4s, and 4. And so the only thing that's missing is the addition of 1. Well, that looks like a shifted version of cosine or sine Laplace transform, but we don't have s plus 2 on the top, and that's exactly what we need to do. We need to break the top into something with s plus 2, so since I added 2, I now have to subtract it. And the first looks like a shifted transform of the function cosine, and the second one looks like a shifted transform of the function sine. So let's go ahead and figure out what's going on here. So it seems like the first one was coming from a cosine, and the fact that we have 1 right here means that omega is 1. So that, and I will explain what the shift gives us a little bit later. So we have cosine t, and we also have to have minus 2 sine t, but because they were shifted, it means that the original function should have been pre-multiplied by e to the minus 2t. So we're shift by negative 2 right here. Okay, that's a Laplace transform of just the fraction, and as I said, we need to figure out what's going on after that. So here I marked where the things are coming from. One is coming from the plus 1 part, because that's plus omega squared, and the negative 2t comes from the fact that s is shifted by alpha negative 2. Okay, the inverse Laplace transform of f of s, therefore, must be, because of the factor e to the minus s in front of it, that means that it has to be the inverse Laplace transform of the fraction but t replaced with, well, I'm going to pause for a second. What should we replace t with? Should be t plus 1 or t minus 1? And the correct answer is t minus 1. So that means that we're going to have e to the minus 2, and t is going to be replaced with t minus 1. Cosine is going to have t minus 1 in it, and sine is going to be t minus 1 in it. And that's not it. There's one extra part that needs to be here. Can you guess what it is? Well, if you did, that's right, it's got to be h of t minus 1. Because we're shifting function by a factor, by a value of 1, that means that everything that comes before 1 has to be zeroed out. Okay, the last few examples that we have here will be concerned with using the Mathematica for doing similar calculations. And I have slightly more complicated versions of the functions here. So let's see what happens. First, I want to just confirm that the Laplace transform that we computed earlier are exactly the same as what we did. So let's plot Heaviside theta of t minus 1 with respect to t from 0 to, well, let's say 5. Well, that's what it does. The function turns on at t equals 1. Okay, now I need to, well, this is what I'm going to do. I'm going to plot Heaviside theta at t minus 2, and I'm going to do it from 0 to 5 as well. So this is the function that turns on at 2. Well, what I'm going to do is I'm going to put 1 minus that, just so that introduce it to the effect that it has. So 1 minus Heaviside theta will be the function that turns off at 2. So if I take my original plot and subtract Heaviside theta with t minus 2 right here, I get exactly the effect that I need. So it's a function that turns on at 1, turns off at 2. And then if I just take this whole thing and multiply it by any function, say, I don't know, sine of 5t, so it's going to be the function that's going to be oscillating somewhat quickly. Well, not very quickly, let's make it very quickly. Let's make it oscillate very quickly, 25t. Well, that's what's going on here. We have a function sine of t, and we just turn it on at 1, turn it off at 2. And this is how you can make piecewise defined functions. So let's take this expression and compute the Laplace transform of it. And as I said, the Laplace transform has to be computed. This way you specify the function, expression, then you specify the variable in that expression, and then you say what variable you want the output in. And that's exactly the result. The result is exactly the same as what we computed earlier. Alright, let's look at the second function that we did. So we did sine of t, but we did Heaviside of t minus Heaviside theta at t minus 2 pi. And here I'm typing escape, p escape, and that gives me a pi. That's in terms of t, and we want the result in terms of s. And that's exactly the result that we produced earlier. It looks a little bit different, but mathematically it's exactly equivalent to the expression we produced earlier. Last example that we did was exponential function of minus t times sine of t times cosine of t. Simple. Notice that mathematics has this peculiar tendency to put the constants first and then the s and then the s squared terms. Well, that's how Mathematica functions, and you just gonna accept it. That's how it's gonna give you the output. Inverse Laplace transforms is computed in exactly the same fashion. We have exp of minus s, and then we have a fraction, we have s, and let me show you something that you might find useful. Mathematica has palettes, and one of the palettes is those assistants when you can just choose different forms. So for example, this form right here gives me a little fraction, and also when you hover above it, it gives you a shortcut how to enter it. So here I want this s to be in a fraction, and then I want s squared, so I use the superscript and it's squared plus 4s plus 5. I would recommend to use these editing and typesetting features sparingly, because it's very easy to enter something that's Mathematica is not actually would not consider as a correct expression. So these two-dimensional formulas, don't get too carried away with them, but they'll helping out when you're trying to read the expressions. This is one of the appealing one of the reasons why Mathematica is so appealing to mathematicians, because math expressions look like math expressions, not like long tedious expressions that are very hard to read. So this inverse Laplace transform, I gotta give it first the letter S, because that's the variable in which the expression that I give it to, the expression that I give to it, has its variable S, and then I want the output in terms of t. And that looks horrible. There's exponential of complex numbers, etc., etc. So the way to make Mathematica to simplify it a bit is to use the command full simplified. I will try to get rid of the complex numbers here. So what we have cosine of t1 minus t, which is, since the cosine is the even function, it's the same as cosine of t minus 1. Well, then there is a sine of 1 minus t, and we had sine of t minus 1, but we had minus 2 sine of t minus 1. Well, that's fine. Sine is the odd function, so when we switch the sign of the argument, the sign itself switches the sign. So that explains the plus 2. Yes, we did have Heaviside function of t minus 1 there, and we had e to the 2 times t minus 1. So everything checks out. So let's look at the functions that I suggested we look. So the first one is the function f of t that's turns on at t equals 0, so it's Heaviside function that it's going to turn on at 1. Then it have to shift to -1. Let's try that. Plot from -1 to 5. So this is the function that jumps from 0 to 1 at 0. Then it has to jump to -1, and the way to achieve it is subtract 2 Heaviside functions, but those functions have to be shifted to 1, and you can see that it jumps to -1, and that has to be all the way, oh sorry, why did I put -2 right here, t minus 1. So this this function jumps to -1 at 1, and then jumps to 2 at 3. So since it's at -1 right now, I will have to add 3 Heaviside functions. And that jump has to happen at 3. And this is what happens. And the function has to be 2 for eternity, forever. So this is the function that we will need to find the Laplace transform of. Okay, I'll pause for a second, try to figure out what's going to happen. So Heaviside t is going to give us 1 over s, t minus 1 is going to give us e to the minus s over s with the -2 as a coefficient, and Heaviside theta at t minus 3 is going to give us e to the minus 3s over s. And that's exactly what happens. It's slightly out of order, but that's exactly the Laplace transform. All right, what about the other function? That is e to the minus t, all from 0 to 2, and then it turns off. So this is a regular plot of the function e to the minus t. Well, I'm going to turn it on at 0. So this is what happens. Well, then I need to turn it off at 2. And that's what happens. So we need a Laplace transform of this. All right, let's think about what's going to happen. Well, t minus 2 is a shift, but exponential function is not shifted. So what I have to do to try to do it by hand, if I had to do it by hand, is I would have to express exponential function at minus t, e at minus t, as e at minus t minus 2, and then there's going to be minus 2. So e to the minus 2 will have to be factored out as a coefficient that is artificially created there to make exponential function to look like a function of t minus 2. So that's what's going to happen there. The exponential function had a very easy Laplace transform. It was 1 over s minus alpha. So in this case, it's going to be 1 over s plus 1 everywhere. And it's going to be then multiplied by various exponential factors. And the factor e to the minus 2s e to the minus 2 is going to appear there at some point. Let's do it. And exactly as I thought, e to the minus 2 is there. So the first function has just a Laplace transform 1 over s plus 1, and then the shifted one has e to the minus 2s because of the shift. But notice there's also 1 right here, and that 1 is simply e to the minus 2 as a coefficient that I predicted would have to be here. Alright, let's look at the examples with the inverse Laplace transform. And to save you from the boredom of going through all of them, you can go ahead and go through all of them. I'm just going to do a couple of them. Alright, let's look at the first one. Capital F of s, e to the minus s over s cubed. Before I evaluate this, let's try to think about what's going to happen. Well, 1 over s cubed would be a Laplace transform that comes from t squared. And e to the minus s means that t would have to be shifted by 1. So it's going to be t minus 1 cubed with some coefficient times the Heaviside function at t minus 1. And that's exactly what happens. Oops, not cubed, squared. Apologize. The second one it was 2s plus 1 divided by s squared plus 9. Well, s squared plus 9 means that it comes from things like sine and cosine of 3t, so omega is 3. Then there is the 2s plus 1, which means that we should have something like 2 cosine of 3t, and then 1 would mean that there's got to be 1/3 of the sine. And Mathematica decided to give us 1/3 of 6 instead of 2, and group it this way. Well, again, Mathematica has a mind of its own, and that's what it does. Alright, you can go ahead and try to figure out the rest of them just for fun and see what happens. And I would recommend you try to first predict the outcome of those calculations, and then evaluate, rather than trying to evaluate and then analyze the outcome. You will develop the intuition this way much faster about the Laplace transforms and what happens with them and how those shifting theorems play as expressions. Alright, that's it for today. Good luck with the homework, and I'll see you in the next video.